I remember this from pre-cal, but I can't think of it.
All right, so if we're doing the arc length bit, so if I have some distance along there, s, and some angle, theta, some radius r, there's a mathematical relationship, assuming the angle is in radians. That's the connection of radians. If the angle's in radians, what is the relationship between these three quantities?
It's gotta be that theta is equal to 2 pi r. Either that or I'm just remembering something wrong.
Right, so what is 2 pi r?
2 pi r is a
The circumference.
circumference.
Okay,
Yeah.
so if I look at the entire arc length of the entire circle, in other words, the circumference, then s is 2 pi r, and the angle is
360.
in radians.
And radius is 2 pi.
Okay, so if my angle is 2 pi radians, then my arc length is 2 pi times the radius.
Okay.
Suppose my angle was only half that, what would my arc length be?
Pi r.
If it was a quarter?
1/4 of.
Yeah. What's the relationship between s, r, and theta?
S controls how much, or I'm sorry, the radius control, you said if the radius was a half, right? Or if S was a half.
If s was a half, it's
Yeah.
half what it
It's
was.
just r
You just
times
multiply it by
theta.
r by the radius,
Well,
What do you multiply times r?
the radians, like.
The angle.
the angle.
So s is equal to r theta. That's the relationship. Standing room only. All right. If we look at therefore the change in, if that's a distance there, if I have something rolling, that's the change in distance equal r times the change in the angle, and it takes place over a certain amount of time. So I have distance divided by time here, which is speed. I have change in angle over change in time, which is angular speed. That's the relationship between v and omega, between speed and angular speed. If I look at the change in speed is equal to r times the change in omega, divide that by however much time, what's my relationship?
Speed is, no. That's acceleration is equal to, r change in angular speed over change in time.
Which is,
Angular acceleration.
that's the relationship. If the rope is not slipping, then the angular acceleration of a point on the rim is times the radius is equal to the linear acceleration of basically the mass. That's the fourth equation, which is going to connect these. So we now have tension 1 minus M1G equals M1A. M2G minus tension 2 is equal to M2A. And then R, sure, we'll do it this way. R tension 2 minus R tension 1 is equal to 1/2 MP R squared times A over R. And now, conveniently, that R cancels out with that. This R cancels out with those. And I now have an equation without R in it. The radius drops away. And so my third equation has been reduced to tension 2 minus tension 1 is equal to 1/2 MPA. And now I can add them. I can add that and this together. What? Tension 1 and tension 2 cancel out. That's convenient. And I'm left with M2G minus M1G equals M1A plus M2A plus 1/2 MPA. This is the driving force. This is trying to slow it down. At this time, not only do I have to get both masses moving, I have to get the pulling moving also. And so that affects the acceleration. And so M2 minus M1, depends on how you want to present this. G is equal to, let's factor A out, then I'm left with, put that last, M1 plus M2 plus 1/2 MP times A. If we were still dealing with this being a chapter 2 problem, this term would have gone away. Because the pulling doesn't have any effect at that point. But we're more sophisticated, we now have this little additional piece. So that is 3 times 9.8 equals 5 plus 8 plus half of 3. Says 13, so 14.5A. Somewhere around 2 meters per second squared. .07.
Yeah, 2.03.
Agree?
Yeah.
Yeah, 2.2.
All right, I handed tests back to some people the other day, but not to everyone. And I'm going to pause the camera just before I end up flashing the greatest for the world to see.